Every time your AI agent responds, you are paying for the words going in and the words coming out. On your bill, you will see those called tokens. The more tokens you send in, the more you pay. And if you send in is not quite right, too much or missing something important, your agent starts to hallucinate. There are 5 techniques to help you to reduce token waste, improve accuracy, and catch failure before users see them. And each one is code change, no prompt change. Let's see. The first one is Semantic Tool Selection. You filter which tools going into the context on every call. The model only sees what it needs for that specific query. 2. Guardrails. For precise query like aggregation, counts, multi-hop reasoning, you replace text retrieval with structured graph queries, and the model gets a compute verifiable answer, not a sample. 3. Multi-agent validation. A second agent checks every response before it reaches the users. Silence failure get caught instead of confirmed. 4. Neurosymbolic Guardrails. Your rules live in Python code, not in the prompt. The model cannot skip. 5. Runtime Guardrails. Steer, don't block. When a rule fires, the agent self-corrects and completes the task. No hard stop, no user retries. For each technique, I will show you the agent without it and then with it, so we can compare. The demos use Travel Agent build with Strands Agents, of course, an open source agent framework from AWS. In this demo, I'm using OpenAI as the model provider, but you can swap it for Vetro, Anthropic, or Llama, or the other supported provider with one line chain. All the code is open source. In the repo linked below, and at the end, I will show you Amazon Vetro AgentCore, AWS managed service for running AI agent at scale. I walk through the architecture and show you where to find everything in the repo if you want to deploy it yourself. Before we start, if you have not seen the previous video where Morgan talks about Amazon Vetro and Strands Agent from scratch, I recommend you to start in there. This build directly on the top of it. And of course, link is in the description. Let's get into it. Our travel agent has 31 tools. Flights, hotels, payment, weather, cancellations. Every time a user sends a messenger, all 31 tool descriptions go into the context window. The model reads all them before deciding what to do. And if your agent has memory that grows to every conversation adds more context that gets sent with every single messenger. And you pay every single one of those tokens whether the model ends up using that tool or not. To understand where those tokens come from, you need to see what a tool actually looks like to the model. In Strands Agent, you write a function with the tool decorator, a name, a description in the docstring, typed parameters. Strands takes that and generates a schema. Name, description, parameters, and that schema is what goes into the context window on every call. Each tool schema is about 17 to 100 tokens depending on how many parameters it has. If our travel agent has 31 tools, that adds to up to somewhere, 3,000 tokens per call, just for the tool description, before your messenger, before the response, every single call. By creating a tool database, we can filter the tools that the agent may need before the agent is invoked. With the filtering, the model sees only the 3 more relevant tools. Token usage drops from thousands to fewer than 300. Let me show you in the code. Before running, open the requirements file. The demo needs a Strands Agent with OpenAI, Sentence Transformer, the local embedding model we use to cover text to vector. This is open source, so you can run that in your computer. We use fast CPU, the local index for similarity search, and Python.f for the API key. Install everything with only one command. Let's do that. Let's come back to the Jupyter Notebook. Here, you can see that I'm using OpenAI as model provider, just right here. To do this, I need to import the OpenAI library, just right here. And Strands use Amazon Bedrock by default. If you don't specify a model, it picks up your AWS credential and use Cloud via Amazon Bedrock. And if you want to use another model provider, for example, Anthropic or Ollama locally, you need to install the requirement for that model provider, as we did before for OpenAI. And you need to import the library for that model provider. In this specific demo, I'm using GPT-4 Mini, and if you want to run Bedrock, you only need to delete this and delete the import library. 2 lines change, everything else stays the same. Now, here in this application, I have the Register app. In Register app is where the filtering layer lies. We have build index that takes your list of tools. For each one, it combines the name and doctrine into a text string and convert it string to a vector using sentence transformer, the model I just showed you before, that you can run locally as open source. And those vectors or tools vectors go into the files index, creating our vector store of tools. And we use search tool that takes the user's message, the user query, to convert it query a vector with the same model. So we can use the query to search the closest tool in the index. And this application returns the actual function object ready to pass directly into the agent. And we use swap tools to make this work across a conversation. This function helps us to add and remove the tools in the agent, and the conversation history stays intact. Only the available tools change using the swap tools. Let's come back to the Jupyter Notebook. Here, I have 3 tests on the same query, and we are using this question, this test query just right here. They are like the ground truth. We know the query and we know the tools that is going to answer that query, because we need to know what is the accuracy of this agent. So I run this. I have this helper function, and let's try it. The first test is with my traditional approach, with all the tools. So I'm going to send all the tools, and for this demo, I am using 29 tools. When you run this, you can see the query and the amounts of token that this agent is using to answer that question. Here you can see that all of those are between 2,000 and 1,000 tokens in each call. Now, let's run the same, but this time with a semantic approach. If you compare the first question, search for something in Paris, the agent is only using 300, almost 400 tokens for this invocation. And the same question in the other agent, the agent is using 2,000 tokens. So yes, we have a difference here. And the accuracy is a lot different as well. For the first one, the agent have 31% of accuracy, and for the second one, the agent is having, a little more. All this invocation, we are using this only, we send a question, the agent responds, and then we are using another invocation to the next question. What happens if we want to have memory? Yes, we use the swap tool application. Let me show you. So here, every time that I search a tool, I do the same. Receive the tools, and I swap the tools. So every time that I invoke this agent, I'm sending all the context and the chat history. And you can see here in this demo that amounts of token is every time more, because you are not going to sending only the tools. You are sending the chat history for the whole conversation. And that's it. In production with Amazon Bedrock AgentCore, you don't need to build this index yourself. This is only a demo that runs in my computer. You can use AgentCore Gateway, the running layer inside AgentCore. It handles tool selection automatically. You register your tools once and it finds the right one for each request. Same principle, no infrastructure to manage. RAG, Retrieval Augment Generation, is how agents access your own data, your knowledge base. You take the user's question, search your document for the most similar content using vector search, and pass what you find to the model. The model answers for that. It works well for open question, find me something about this topic, but there is a category of question where RAG breaks down. What is the average rating across all hotels in Paris? How many hotels have a pool? Vector search always returns something, even when nothing is truly relevant. And the agent only sees the top end chunks for your all data at a time. It cannot aggregate, can, or traverse relationships across the full dataset. So it estimates, and it presents that estimate as a fact with full confidence. Here, let's see a comparison. Left side, RAG retrieve 3 chunks from 300 documents and the model guesses. Right side, Graph RAG runs a query across all the data and returns a compute resource. Graph RAG addresses this differently. Instead of retrieving text chunks, small little pieces of your data, you can build a knowledge graph from the documents. Nodes, relationship, structured data. And for this demo, I use Neo4j locally, and the model, my tool, writes a Cypher query to search in my graph database. Cypher is Neo4j query language. It's similar to SQL. Yeah, similar but it's not the same. And the graph runs the query across all the data without use tokens and without use the model. And then the model gets back a compute verified results. No, a sample. Let me show you that. First, you need to install the requirement. We use, again, Strands Agent with OpenAI, Neo4j, Neo4j Graph Rack, FICE CPU, because we are going to compare two different agents. One that use vector store, or vector store is going to be FICE, and we use again sentence transformer to do the vector embedding. For my demo, I already have the graph built for this demo, but in the code I share with you how you can build it yourself. Let me show you. You can use build graph lite for a little version that only use 30 documents to build the graph a knowledge base, and you can use the normal version of the app to build the database with the graph base with the 300 documents. Let me show you. The repo has step by step to set up everything for you, and this is specified to Neo4j. Remember, this only works with that. And to build this knowledge graph, Neo4j allows you to use a LLM that can understand your data, and it creates the nodes for you, so you don't need to hardcore the node for this graph database. This is only specific to Neo4j. The LLM here in this demo is OpenAI, but this library also supports Anthropic, Mistral, Olama, and of course Amazon Bedrock. The key thing here, remember, you don't need to define the schema because the LLMs read tests and discovers the entities and relationship by itself. Let's test it. I have two agents, same model, same data. The RAG agent has a tool that searches by similarity and returns the closest chunks. The graph RAG agent has a tool that runs Cypher query against Neo4j, same model, different tools, different data access. Let's see. Here is my FICE data store. I have 300 documents for that, and for Neo4j, I have 296 hotels in my knowledge graph. So I have my tools, the one that allows my agent to search hotels using vector similarity, and the other one capable to create and run the Cypher queries. I run this, and first test, aggregation. Average guest rating across all hotels in Paris. What is the average guest rating across hotels in Paris? That's my question. So I run this. I have my Strands agent for RAG and my Strands agent for graph agent. So let's see. My first agent, it says the average guest rating for hotel in Paris based on the available data are as follows. So this agent uses the word Paris to search in my document data, in my document vector store. So it receives two different hotels. But the thing here is my LLM, my agent, is the one who is doing the calculation here. And this, what happens if I have more than 2 or 3 hotels? The agent is not going to use the other hotels to do this calculation. And it's doing all the calculation to calculate the average guess rating, blah, 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 blah. So it generates the question. For the knowledge graph, I only have the answer because the agent, it already have the average ready to use. The agent don't need to think mathematical things, and the agent is doing this calculation, not the agent. The tool is doing this calculation using all the data in my nodes. Now, the second one, precise counting. How many hotels have a swimming pool? How many? Let's run our test. For my traditional rack, I receive the available data did not mention any hotels in Paris with swimming pool amenities. So blah, 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 so it gave me a lot of words there. I only ask you how many. If you don't have the data, you don't need to generate tokens there. And the other one told me, the rough rack, there are no hotels that offer a swimming pool as amenity. I have the question twice. But that's it. The graph, the tools, it do the Cypher query, and the answer was 0. No swimming pools here. So that's it. The agent don't need to give me nothing answers. Now, test 3, out of domain detection. Let's see what has happened here. Tell me about hotels in Antarctica. Spoiler, there are no hotels in Antarctica. There are 0 hotels there. Let's see what has happened. So let's run. Let's find agents for the best answer. So, a traditional rack agent say, it seemed I didn't find any specific information or hotel for accommodation option in Antarctica in the available data. But it say accommodation options in Antarctica, they don't have data, but it recommend me to search for searcher station, expedition cruise, luxury lodge. Come on, that no exists there. It's hallucinating an answer for me. That's a normal behavior for these types of agents. So it starts to hallucinate answer when the rack, the similarity search, didn't give you an answer that can use to answer a question. Let's see what is happened with my graph and rack agent. So it ran the query and it received 0. There are still no hotel listed in Antarctica. It appears that there may be limited or no accommodation officially registered in the region. And the other one, it gave me some recommendation to do my search. So that's it. You can run this code, you can compare, you can use another data set to run your test. Everything is there. So when to use rough rack and when to stick with regular rack. Please use rough rack when you want to count, average, multi-hop reasoning, anything that requires a precise answer. And when to stick with rack, come on, it's not so bad. When you want to answer open question, fuzzy search, and structural tests. But the best system use both. Sometimes an agent fails and nobody finds out. It calls a tool, the tool returns an error, the agent does not surface that error, and it generates a confident success response instead. The user thinks it worked, but it did not work. The agent adds and validates its own output in the same loop. There is no separation, no second option, so when something goes wrong, it rationalizes and tells you it worked. Here is what's happened inside a single agent where it failed. It calls the tool, get the error, rationalizes, and returns success response. The user never seen the error. You can address this by adding a validation layer. A multi-agent validation. 3 agents in sequence, 1 acts, 1 checks, 1 approves or rejects. Strands has a built-in class for this called Swarm. It manages the handoff between agents automatically. You just define the role of each agent in its system prompt. Let me show you how. Let's go to the Jupyter Notebook. For this demo, you only need the Strands agent for OpenAI, so you don't need to install another one. So I'm going to run my OpenAI key. The key important here is the swarm from Strands Agent multi-agent library. This is what lets you connect multiple agents in a chain and manage handoff between them automatically. Without it, you will have to wire the agents together manually. Let me show you how you can create your Swarm agentic application. In this demo, we are going to use 3 different agents. The executor, who is going to call the tools and process an initial response. The second one is the validator, who is going to validate the answer that execution just received. For example, is the right tool? I received the right answer for that tool. And the last one is the critic, who is going to approve or reject the answer. And to create our swarm, we only need this line. We swarm our 3 agents, the executor, validator, and critic, and we can add a mass handoff. So in this time, we are going to use 6 handoff. So the swarms handles the flow between them. You don't need to do nothing else. Now, for this agentic fight, we need to compare a single agent with our multi-agent application. For that, we are going to use 4 different scenarios. The first is validate booking. Book Grand Hotel for Alice for 2 nights. Then we are going to try to book the luxury resort for Bob for 1 night. And then we want to book the Paris for Carlos for 3 nights. And the last one is missing booking log up. And we are going to send the query get details for booking. This is a scenario we run through. So for the first one is true and false for the other one. So we are going to compare the results between the single agent and our multi-agent. Let's see what is happening. In the comparison single agent versus multi-agent swarm, you run the code and let's see the fight. So you can see that for the single agent, everything is correct. But we know that that's not the right answer. And for the multi-agent swarm, we have some clear verdict, some hallucination or reject, and one missing the issue. What we have here, the executor gets the error, the validator catches it, and the critic rejects it. So the user never sees a fabricated response. With a single agent, we have like a no entry and return success. So every time is going to be success. For the swarm, executor get the error, validator says, hey, come on, hallucination, and critic reject. The user sees a clear failure, no fabrication confirmation. When you use multi-agent validation that catch fabrication after they happen. You have a rule for your agent. Let's say maximum 10 gas per reservation. You write it in the system prompt, you even write it in the tool description, and the agent still calls the tool with 50. This is not because it is ignoring you, it's because prompts are suggestions, no constraints. The model processes them as text, not as a logic it has to execute. Only code executes logic. A rule in the prompt, the model reads it as suggestion. The rule in the code, the model cannot skip it. Neurosymbolic guardians put the rules in code. Strands Agent has a special feature called hooks, functions that strands call automatically at a specific moment in the agent loop. In this case, right before a tool executes. So you write a rule, check the parameters, and if it fails, you cancel the call. Let me show you what that looks like in the code. The key important in this demo are these three things. We have the hook provider, is the strands base class you extend to create a hook. We have the hook register, it's what strands passes you to register your callback. And before tool call event, it's the event that fires every time the model is about to execute a tool. That last one, it's what makes it possible to intercept the call before it runs. Let's compare. Left, rule in the prompt. The model reads it as text. It may follow it or not. Right, rule in the code. Python executes it. The model cannot skip it. Each rule is a data class with a name, a condition function, and a message. The condition takes a context, dictionary, and returns true or false. Pure Python code, no model code. Let's see the agent here. I go to my Jupyter notebook again. I'm going to show you with you everything so you can run it by yourself. So let's see the agent. To create the agent with hooks, first you need to define the symbolic rule, the rule that is going to be in the code. So you do that with this. We have our rules. Let me show you the rules. These are the rules that the LLM is going to take to give us a decision. So we have the condition function and we have the rules. For example, name, validate dates, condition, validate checks, code. You must have check-in, check-out, and message. Check-in must be before checkout. Yeah, right? And let's come back. We run this. Then you create a validation hook using the register hook, using the before to call event just right here, using the rules that I just showed you. Then we define the clean tools for booking hotel, process payments, configure booking, everything is there. So those are the tools that the agent is going to try to invoke. And step 4, we create the agents for competition. Because this is a fight between an agent with hook and an agent without. And this agent is going to fight using different scenarios. So we have the scenario who is going to confirm booking without payment, book hotel existing guest limit, valid bookings, and each scenario it have the answer we should expect. Let's run the first test. Confirming booking without payment. Confirm booking, blah, blah, blah. So, has been successful, execute. Without hook, it confirmed the booking. But what happened when I have the hook in my agent? It seems that payment for booking needs to verify before the confirmation can be processed. Will you like to process the payment? If so, blah, blah, blah. Of course, I'm not going to book in something if you didn't pay. So the code is actually there. Book hotel exceeding guest limit. The limit is 10. So let's run this. I want to book Grand Hotel for 50 people buying the date. The Grand Hotel has been successful booking for 50 guests. Come on, man. I just told you that the max of our rooms are 10. So it's another error here. And when I using my hooks, the agent said it appears that the Grand Hotel has maximum limited for 10 guests per booking. And booking must be made at least 1 day in advance. Oh yeah, that's another thing that I put in there in the rules. When you are not using hooks, all rules pass. Probably it's going to block something if they use the prompt in the right way. In this demo, just use the same model, same tools, and the same prompt. I didn't change the prompt for my agents. The different outcomes is because the rules are in the Python code, in the hook, not in the prompt. This pattern of enforcing rules in code before tools run. And it's also what Amazon AgentCore policy service does at the infrastructure level. The same concept, but managed for you in production. Hooks are all or nothing. They block, but something you want to agent to adjust and keep going, no stop and leave the user waiting. That is what I'm going to show you in the next chapter. Hooks block unconditionally. The agent stops and the user has to try. For a hard constraint, that is exactly what you want. But sometimes the rule is softer. Maybe a room fits for 4 guests, but a group of 6 could book 2 rooms. Or a flight is full, but there is capacity on the next one. You don't want to block everything. You want the agent to find an option and complete the task. That is steering. Here on the left, the hook fires and the task fails. It blocks. On the right, agent control steer the model and the task complete. The other difference is operational. With hooks, changing a rule means changing code and redeploying. With agent control or steering, which is the name of the open source library used here, rules are registered on a local server via API. You only have to update them without touching the AgentCore. The agent picks them up almost immediately. Let me show you that in the code. This demo needs one extra packet, the AgentCore SDK for Strands Agents, the framework that we are using here. And you need to run the setup controls once before the demo to register the steering rules on the local server because we are going to create a local server here in my computer. In the setup control, you can see all the rules that this agent is going to use to do the steering. So we import the agent control client, the agents control, and in here the control rules. So the name is steer max guess, for example. So the definition is guide agent to reduce guess count when exceeding maximum of 10. We have another one that it say deny no payment. So block booking confirmation without prior payment. That's a hard rule. And yeah, we can put hard rule here in our steering configuration. Here in my Jupyter notebook, where I create my agent, I have two key importance for the agent control SDK. I have the agent control plugin that captures agent events and sends them to the agent control server or rules. And we have the agent control steering handle that is listened for a steering decision for the server and delivers them back to the model. Together, they are what connect a Strands agent to the agent control steering logic. Now, let's see when we compare both approaches side by side. The hook version with mass guess hook that cancel the call if we have more than 10. And the agent control version with the same agent, same tool, but two plugins added. One captures events, one delivers the steering messages back the model, and the steering rule is registered on the agent control server. So let's test with my agent with hooks. We have the mass guess hook that block everything else that exceeds maximum of 10. So I run this and I'm going to send the query. And the query is book Grand Hotel for 50 guests. The agent runs the hooks and it blocks the calls because the maximum is 10. So with agent control, you remember that it can steer if I have more than 10 people that want to use the room. So let's see. We have our libraries here. We have the agent. We need to initialize our agent control server. We have the plugin. We have the steering. And that's how we create our agent with the steering rules. So let's run this. How do you take this to productions without managing service, without building infrastructure? That is what I will show you now. Everything we built in the previous demos runs locally. For the production version, Amazon Bedrock AgentCore gives you a runtime, a gateway, short-term and long-term memory, and CloudWatch observability built in. No servers to manage. Here, this is the code for all the demos I just showed you, and you will find the architecture. The Strands Agents run inside the runtime. The gateway routes tools calls to Lambda function automatically. The Lambda functions are going to be our tools. The steering rules from previous demo live in DynamoDB. So you send them there and they are live on the next call. No redeploying needed. And for Neo4j, you can use AuraDB as an external graph database, which also has a free tier. The code is here in this repo. You will need AWS credential with Bedrock access. If you are new to this, start with a notebook. I have a notebook ready for you so you can deploy everything. And if you are comfortable with infrastructure as a code, there is also a CDK stack, a cloud development kit, to deploy everything at once. Both options are in the repo. To go deeper on AgentCore, Morgan has a full video link in the description. Don't stop at the demo. Try going to production with Amazon Petro AgentCore. Let me bring it all back. Token weights on every request. Run tool picks. Fabricate confirmation. Rules the model. Guardrails skip it. Hard blocks that stop the user instead of helping them. None of those are prompt problems. All of them are addressable in code. 5 techniques beyond the prompt. All the code is in the repo linked below. Each demo has a notebook. Start with demo 1 through demo 5. Each run about 15 minutes. For demo 6, you will need AWS credential. Have you tried any of these in your agents? I would love to hear about in the comments. See you in next one, and happy building!